Hi, and welcome to Probability Distributions Day 5. Today we're going to be talking about normal distribution. The normal distribution is probably the most important distribution in statistics. It is a suitable model for many naturally occurring variables. It is used with continuous data, unlike binomial distribution. Um, think of IQs, heights, weights, SAT scores. All those kinds of things are normally distributed. So that's what we're going to be using when we're talking about these. Um, some of the characteristics are the curve is a bell shape. It is symmetrical about the mean. The mean, median, and mode are the same. And there's no single normal curve, but a family of curves that defined by the mean and the standard deviation. So every curve will look a little bit different, except they'll have the same basic shape. So if a random variable x has a normal distribution with a mean of mu and a standard deviation of sigma, then it's written as this, the x with the squiggly, normal, mu, sigma squared. Remember that sigma squared is the variance. Okay, so that's the variance, but when we're looking at these, the actual sigma value, they don't square the number, they just put sigma squared so you can see the standard deviation. Okay, so here I have some examples here. The graphs um, show x1 is when my mean is 5 and my standard deviation is 2. X2 in this first set is when my mean is 10 and my standard deviation is 2. And X3 is when my mean is 15 and my standard deviation is 2. So if you notice, all of these standard deviations are the same. However, the means are all different. Therefore, the widths of the curves are the same, but yet they've shifted left and right on the axis. For the next set of 3 graphs, um, my mean is 5 for all of them. The standard deviation is 1, 2, and 3. And that means that all of the curves are centered at 5 in this case, but their height is going to be determined by the standard deviation, depending on what it is, how closely grouped the data is. So the curves may have different means and or different standard deviations, but they all have the same characteristics. The area beneath the normal distribution curve is the probability. So underneath the entire curve, the area would be 1. And we will consider partial areas under the curve to help us find the probabilities we are looking for. So we're actually only going to be looking for part of the area under the curve, so we usually draw a picture to help us out to see if our answers make sense. And we're going to be using our GDCs, graphing calculators, to do these problems so that our life is much, much, much easier. So the standard normal distribution is the normal distribution where mu is 0 and sigma is 1. So my mean is 0, my standard deviation is 1. This is standard normal. Okay, that's not normal distribution, it's a standard normal distribution. In this case, the random variable is called z, and it uses z values to describe the number of standard deviations away from any value it is from the mean. So a standard normal distribution is written as z, not x. Okay, so for example 1, we are using a standard normal distribution. And these are just graphing calculator problems. So we need to use what we're going to call normal CDF, and it's right in the same menu as the binomial CDF. It's the first, I think it's number 2 in that second VARS menu in the distributions. So for part A, in order to type that into the calculator, we're going from -2 to 1. My z-values are -2 to 1. So I'm going to type in normal CDF. And the first thing that I'm going to put is my lower bound, which is -2. And then I'm going to put my upper bound, which is 1. And my mean is 0. Or sorry, my mean is 0 and my standard deviation is 1. So I just simply type that into the calculator. And I will get 2366.819. For B, if it's less than 1, all right, so let me go back to A here and draw a picture. This is at 0. So here's 1, here's -2, and here's 1. So we're finding the area here. And for B, this is 0, so this is 1. We're finding that area. So my lower bound, we don't actually have a value for that. Technically, it continues on forever. We put in -E99. That's what I type into the calculator. And that just kind of like telling it negative infinity. And then I use 1 because my upper bound is 1, and 0 and 1 for my mean and standard deviation. And when I do that, we have 0.841. And that makes sense because I have more than half of my curve, so therefore I should have more than 50%. For C, that's 0. There's -1.5. That's just this small area over here. So it is normal CDF. And my, oh dear, my bad, that's greater than. Yikes. Let me erase that. Hang on. Okay, there, I changed colors so you can see what I fixed. It's everything greater than -1.5. So my lower bound is -1.5, but I don't really have an upper bound, so we do positive E99. And then I do 1 and 0. And when I do that, the 3 sig figs, it's 0.933. And for D, if I draw a picture for D, that's 0. And anything less than 0, I really don't even need my calculator to calculate that because it's half the curve. But if you didn't realize that, normal CDF, and my lower bound is -E99. My upper bound is 0, and then I have 1 and 0, and that would be 0.5. And for part E, the absolute value of z is greater than 0.8 means -0.8 less than z less than 0.8. So it's giving me a range of numbers. So I'm going to do normal CDF and CDF. My lower bound will be -0.8. My upper bound will be 0.8, 1, and 0. To draw a picture of what that would look like, This is 0, negative 0.8, 0.8. So that'll be everything there. When I type that into my calculator to 3 sig figs, I'd get 5.576. Okay, so that's all really just calculator work. So probabilities for other normal distributions when mu is not equal to 0 and sigma is not equal to 1. In these cases, we can standardize any normal curve by finding the z values using the formula z equals x minus mu over sigma. We've done this before. You did this in Algebra 2 Trig. However, it's not always necessary. You can use your graphing calculator to find the probability without normalizing the curve. Oops, that should be G there, not enough. It's one of those things where you can always standardize any normal curve. It's never wrong to standardize a normal curve, but it's not always necessary to do it. But it's never wrong to do it. So you have options. All right. I'm going to show you how to do it by using the z-scores and then show you how to do it without doing the z-scores. So we have the random variable x, which is normally distributed. My mean is 10, my standard deviation is 2, and I'm trying to figure out when my probability is between 9.1 and 10.3. So what I need to do is, if I draw a picture of that, since my mean was at 10, and 9.1 will have to be, you know, over here somewhere. And then 10.3 would be above there a little bit. So this is really the area that I'm looking for. But I want to figure out what my z-scores are. So z is equal to x is 9.1 minus mu, which is 10, over the standard deviation, which is 2. So in this case, now if I'm less than the mean, I'm going to be negative for my z-value, because z values start at negative, pretty much -3 and go up to +3. But if your mean is at 0, what we're doing is we're taking our curve and we're shifting it, so our mean is 0. So what's going to happen is we keep our mean, and our picture is actually going to look the same, but we're finding new values. So when I put that in the calculator, I'd get -0.9 divided by 2, so it's -0.45. So that's what this value is here. And then I'm going to do another z-score. It's 10.3 because that's x minus mu, which is 10, over sigma, which is 2. So this would be 0.3 over 2, which is 0.15. So I still have the same picture. It's just that I have different values on the bottom. So when I go to type this into my calculator using the z-scores, I would type normal CDF. My lower bound would be -0.45. My upper bound would be 0.15. My mean is now 0. And my standard deviation is now 1. And when I type that into the calculator to 3 sig figs, I'd get 0.233. Now, like I said, you don't necessarily have to do all that changing for the problem. And I'm still, so this is using the standard normal curve. And this is just going to be a good old normal curve. So just use the information that we were given, that we had, and we're still going to keep it normal CDF because that's not changing. My lower bound was 9.1. My upper bound was 10.3. My mean was 10. My standard deviation was 2. And if you type that into the calculator, you still get 0.233. So either way, it doesn't matter. You're going to end up with the same answers. There will be times where we do have to standardize. When we're comparing two different sets of data, you have to standardize the curves because that way you're comparing apples to apples. Otherwise, you're comparing apples to oranges. If I were to take and compare ACT scores with SAT scores, I'd have to make sure that I standardized the curves so I could see which test I did better on. So that's what we're looking at. Basically, all we did today is just calculator work. And when we come into class, we're going to get familiar with using the calculator work, the calculator. Next, we'll actually do examples of how we apply this. All right, see you in class.